So how do we know when a linear system is in the simplest possible augmented matrix form? So the simplest possible augmented matrix form is called its reduced row echelon form. So because that's a mouthful, we often just call it RREF by its initials. And so 4 things have to be true for a matrix to be in its reduced row echelon form. The first thing that needs to be true is that the first non-zero term in every non-zero row. Right, so if I start reading my rows from left to right, and I start with all zeros, the first non-zero entry that I hit as I'm reading each row from left to right needs to be a 1. And that number, that 1, is what we put a box around and call it a pivot. We also require that each pivot is to the right of every higher pivot. So we can never have, coming back to my whiteboard for a second, I would never put a box, for example, here, if there is a box to its left underneath it. So this is not something that I would want to do, right? That as I read my pivots in my matrix, they should be kind of going downward and to the right. I should never find another pivot that's sort of hanging over my previous pivots on the right-hand side. So we require every pivot to be to the right of every higher pivot in the matrix. The third condition is that every term above or below a pivot is 0. This is why I call them the hammers. They're going to be the ones that we use to cancel out everything above them and everything below them into zeros. And then finally, the last thing that we require is if there are any rows of my augmented matrix that are entirely 0, so on the left and the right side of the vertical bar, we want to just swap those rows all the way down to the bottom of my augmented matrix. And if all 4 of these conditions are satisfied, then we call the matrix in its reduced row echelon form. So when it says above or below a pivot, I think the intention is above and below a pivot needs to be 0. Because after all, if we have a pivot, it has the capability to cancel out everything above it and everything below it. And so we want to be able to have done all of that cancellation before we can say that our reduced row echelon form has been achieved. Yes, so each term above and below a pivot ought to be 0. So notice that in the process of doing this row reduction before, they put some squares around entries that didn't satisfy all 4 of these conditions to be pivots yet, right? I mean, I guess it did according to our definition of pivot. The leading term of each non-zero row is 1, and every pivot is to the right of every higher pivot. So that's already true at this stage of the game, right? The first non-zero entry left to right on this row is this one, and it's a 1, so that's a pivot. And then the next non-zero entry on this row is this one, which is to the right of the one that's above it, so that's also a pivot. But this one can't be a pivot because it's not to the right of the pivots that are above it. And this one can't be a pivot because it's not the first non-zero term on its row. So I can't put a box around either of these unless I'm somehow able to, let's say, cancel out this one. If I can cancel out this one, then maybe there'll be a 1 here, or maybe I can get there to be a 1 here that I can make into a pivot. Generally, we can identify a pivot before we've gotten the zeros above and below it, right? So even at this stage of the game, we could identify that this 1 is going to be one of our pivot positions. We just haven't used it yet at this point to cancel out the entries above it and the entries below it. This step succeeded in canceling out the entry above it. And if I did one more step, let's say row 3 minus row 2, with the result getting stored in row 2, that's going to cancel out the one that's below it also. And so after that step, which again, now I've done a different final 2 steps than the authors of the original exercise did, which is okay. When I do row 3 minus row 2, I'm going to have 0 minus 0, so nothing's going to happen there. I'll have 1 minus 1, which achieved the cancellation that we were hoping for in that entry. And then I have 1 minus 2, which is negative 1. And 1 minus 4, that gives me a negative 3 over there. And I still have my 2 pivots there and there. Right? But I don't quite have a new pivot here yet. I need to do one more step before that becomes a pivot. What should I do to make this last entry in this position here into a pivot? Because it's not currently one. What's a valid operation I can do to turn this into a 1 instead of a negative 1?
Multiply it by negative 1.
Yeah, multiply that whole row by negative 1. Negative 1 times row 3. And if I do that, this becomes positive 1, that becomes positive 3, and now that 1 down there satisfies all the conditions that a pivot needs to satisfy. And again, we can identify it as such, as a pivot, before we've used it to cancel out everything above it. And it looks like I have inadvertently made a copy error. There are so many ways to mess up row reduction when you do it by hand, which is why this is the only section where I'm going to expect us to do that, and after that, technology is in play. Was that your question? Or do you have another one? The question is, would it have made sense to have swapped the second and third rows? If I wanted this one to be a pivot instead, I could just swap it up into the second row, and the second row goes down to the third, and yeah, then that one would be a pivot. So there's a couple of things that I would say about that. The first is that generally when I'm using these row operations, typically row swapping is one of the last things on my mind. I try to do row swapping only when it's absolutely necessary, and I try to do it toward the beginning of the process. But it's always in play, and you can always do it. It gives us an equivalent solution. Another thing that's true, and I think kind of interesting, is that the number of pivots that we get in the process is actually more important than where the pivots actually end up at the end of the day. As long as they still satisfy the criteria for being pivots, that they're the first non-zero entry on a row and they're to the right of every other pivot that are above them, then the number of pivots is the thing that matters the most in the process. So what we have in this matrix is not all the way down to the reduced row echelon form yet. Because it satisfies condition 1. We've identified all the pivots. All the pivots are to the right of every higher pivot. But we haven't yet satisfied condition 3, that every term above and below a pivot is not yet equal to 0. Just because of these two entries that are still here. So let's just finish up that process. Do that last step that would be necessary to take this matrix into its reduced row echelon form. And I'm going to do both of these steps at once. I'm going to use this pivot as my new hammer, right, to get rid of this 2. And to get rid of that -3. So to get rid of the -3, I'll just add 3 copies of my third row into my first row. Right? That's going to turn this into a 0. And to get rid of this 2, I will subtract twice my third row from my second row. And so this 1 is going to multiply by -2 and add into this 2 to 0 that out. And at the end of that process, my 3 pivots are still standing. That's another nice thing about pivots, is that because we've arranged them as pivots get arranged, once they become a pivot and once you start using them as pivots to just cancel out everything above and below them, their entries never change. They remain 1 for the whole rest of the process. And then we have zeros underneath them, and we also have zeros above them. And so the only question is what shows up on the right-hand side. And so on the right-hand side, when I do row 1 plus 3 row 3, that's going to be -5 plus 3 times 3. So -5 plus 9, that's going to be +4. So that's my entry in the first row. And then the second row, row 2 minus twice row 3. So 4 minus twice 3 is 4 minus 6, that's -2. And then my third row remains the same. So now that we've gotten it down to this form, here are my pivots. Everything else above and below the pivots are all zeros. And any row of zeros that exists is at the bottom of the matrix. Well, there's no total row of zeros here, so I already satisfy that condition without having to do any work. So this is now the reduced row echelon form of my augmented matrix. And that's going to be the form that once we have it down into that form, there's no more row operations that we can do to make it any simpler. And so that's the time at which we are ready to move toward that final description of the solution set for the linear system. So from the level of overall strategy, yes, I do say that working left to right, top to bottom is usually the way that works best. And sort of we want to give ourselves the fewest number of sort of repeat steps where we're kind of going around the mountain over and over again. And going left to right, top to bottom is a good way to do that. So if we just sort of look at how the authors did this row reduction, we can maybe pull out of their work here what their strategy was. So we didn't have any zeros in this beginning matrix at all. And creating zeros is supposed to be the name of the game. So the first thing we wanted to do is try to get a pivot in the first row. And a pivot in the first row is going to have to occur at the leftmost non-zero entry. But since we have non-zero entries in this first column, we know that that first pivot is going to happen in that first column. So we just want the first entry in that first row to be equal to 1, and as soon as that happens, we can consider that to be our first pivot. And so we put a box around it. It becomes the hammer that we use to nail down zeros in the whole rest of that first column. So you get a pivot in your first row, and then use that pivot to wipe out the rest of its column, which is usually everything that's underneath. Right? And then you turn your attention to the second row. And so probably at this stage, and that happened in this example, in the second row, you'll already be able to see a good candidate for a pivot because, again, the value is 1, and if it's not 1, you can multiply by a constant to make it into a 1. And then call that your pivot because it's to the right of the pivot that's above it, and it's the first non-zero entry on the row because we already zeroed out everything to its left. So we'll call this our second pivot, and then we'll use that as the hammer to kill off everything else in its column. Now, in that process, you can sort of do this in whatever way you like. It looks like the authors of this exercise, this example, sort of after they use this first pivot to kill everything below it, they use the second pivot to first kill out something above it. It doesn't really matter, right? I think that you can make an argument for kind of using each pivot. Once you know that it is going to be a pivot, use it to just cancel out the whole rest of its column before you even move on. So you're kind of going column by column and saying, if this column has a pivot, I'm going to use it to wipe everything else out. If for some reason I don't get a pivot in this column, then I should try to go to the next column and see if I can get a pivot there. Right? And we didn't see that happen in this example, just because in this particular example, every one of our columns to the left of the augment bar had a pivot in it. Right. So we were able to find a total of 3 pivots and use them to zero out absolutely everything that are above and below them. And just to kind of set the table for where we're going, if we take this reduced row echelon form and convert it back into equations, instead of an augmented matrix, let's convert it back into equations. If I call the variables x, y, and z from my original system, then what would this reduced row echelon form tell me about x, y, and z? What would be the equations that correspond to this simplest possible augmented matrix?
X equals 4, y equals -2, z equals 3.
Yeah, because these coefficients of 1 are now the coefficients of x, y, and z. So it's 1x equals 4. And 1y equals -2, and 1z equals 3. In other words, this reduced row echelon form is telling us that x must be equal to 4, y must be equal to -2, z must be equal to 3. Those are the only x's, y's, and z's that give us a consistent, that satisfy all 3 of these equations. Because the solution set of this augmented matrix's associated system is obvious, and because if we retrace our steps all the way back to the original, all of those are equivalent to it because all we did was apply elementary row operations. So once we're in reduced row echelon form, that is the time to translate back into equation form because you're not going to get a simpler expression of how do we determine the values of our variables decoupled from one another maximally, right? The original system, the x's, y's, and z's are all kind of in the same bucket in the equations, and so they interdepend on one another so much. And so the process of doing these row operations is the process of untangling the x's, y's, and z's from one another, decoupling them from one another, so that we can try, if possible, to get an x just by itself in a row, get a y just by itself in a row. And if we can do that for all 3 of my variables, then we're going to have a unique solution, right? Whereas if there are some variables that I can't do that with, then those variables are probably going to depend, there's going to be no way to totally, untangle the values of those variables from the values of other variables. So the process of row reduction is a process of discovering these pivots and then using the pivots to get us into the reduced row echelon form. Once we're there, translate back into equations, and then if it's necessary to do so, those equations can then tell us how to go back to the solution set version, a la the first example that we talked about today. Once we talk about how to assign your free variables, your meaningless parameters, and your bound variables, which is, we're on the precipice of getting there today.